developed a guitar tuner using Microblaze processor.
Alright, so for our guitar tuner, we are using the Nexus 2 board, and then we decided to use the PMod 81 after a little while, because at first we were planning on using the PMod mic, and then we ran into a few problems with that, which we'll explain later. So the guitar tuner takes in the sound signal using the PMod 81, and the 81 converts the analog signal to digital data, and then the data goes into the Nexus 2 board, where we actually use the fast Fourier transform algorithm, which we found online. We tried a few of those because they're all pretty complex and they all involve iterative sine and cosine functions. And so we weren't able to write our own, but we tried a few different FFT algorithms and found the best one. And then we were able to find the fundamental frequency of the sound coming in. And so with fundamental frequency, we were able to display it on the LCD with the Nexus 2 board. And then it'll show which note you're closest to the note that you're playing and how far away from that note you actually are. So by knowing how far away you are, you can tell if you're sharp or flat, and use that to tune your guitar to the note. And then as a hardware reset, we use button 1 on the Nexus 2 board to reset all hardware and start.
So here's our block diagram. As you can see, obviously we've got the standard Microblaze processor with VRAM, and then we use SPI to connect to the PMod 81, and then typical LCD interface, and button for system reset.
So as the design overview, first we had a pretty standard initialization of things. We initialized the LCD screen so we could output data to it. We initialized the buttons so we could use them as the hardware reset. And then we had to use the SPI interface to initialize the 81 so we could actually take in the analog signals and convert it to data which we could use to figure out the fundamental frequency. And then one of our biggest problems was figuring out a good fast Fourier transform algorithm to use. And a lot of that was digging around with code online. They have a lot of FFT algorithms that you can use, and there's a bunch of different ways to do it. Some are faster than others. Overall, it actually takes a really long time. So that's one of the biggest flaws in this design. Not really a flaw, but it takes a long time to calculate the frequency, so you can't pull as fast. You have to pull and then wait. I'd say it was about a second and a half. It's fastest way to get it, until it can actually pull the sound again to try to figure out the next frequency. So we had to mess around with the FFT algorithms a lot, but we did end up finding one that works fairly well. And like we say, it lasts about, calculation takes about a second and a half, so you can pull fairly quickly. And then we just displayed all the information out onto the LCD screen so that you could see what frequency sound you were making and how far away from the note you were.
Okay, so this is the status of our project. Initially, we tried taking audio data with PMod mic, which is basically it's a microphone with a preamp, and then it feeds directly into an AD converter. But we weren't able to get that to work. We couldn't get a clear signal out of it. So then we switched to the PMod 81, and we got much better results there. You can definitely tell what frequency is coming in. So currently, data is being entered and taken out of a fast Fourier transform algorithm. We finally found one that worked for us.
This last one was just, we have a few different ways actually of testing it out. And so you can, because the mic wasn't working very well, originally we were just playing the sound into the mic, and then the mic would have to figure out what frequency it was and then let you know what note you were playing. But we think there was too much outside noise going into it because it was coming out with really jumpy results, and you couldn't get very solid. Like anytime you played the same note over and over again, you weren't really getting consistent data. But we started, like as we switched to the PMod 81, we were able to use an actual cable. We could hook it right up to the cable, so you didn't have as much outside noise you did with the PMod mic. And then from there, we even actually interface it with the computer, so you can play a sound and have the computer capture it on its microphone, and then connect the computer up to the 81 and take that data in, and that actually has a lot less outside noise using the computer's microphone than the PMOD mic did. So that was one of our first. It actually made it a lot better. You had much more consistent data coming out. And then the most consistent data we found was a straight hardware connection with a cord right from an iPhone or any sort of mic that has an amp on it out to our PMOD one. So we have an iPhone app that actually has a pitch pipe and will display different frequencies on it. So you could use that pitch pipe to play a note and then play a guitar and try to match them up. But if you play the note and then hook your cable right up to the iPhone, it has to come directly out and we'll send it right into the PMOD 81. And it was extremely accurate with that. Once there was absolutely no outside noise to have to worry about, we're pretty much dead on with the frequencies. It comes up exactly the same one, which was the best. So this is basically the most you can limit the amount of outside noise and interference, the better frequency data you're getting out.
You showed the demo, but then,
Yeah.
so what were your sources actually?
Okay, so currently we've got it working with two sources. One is more of a a demo just to show that we can determine which frequency is coming in, because obviously you're not going to send a tone generator signal into a guitar tuner, because that's not the purpose of it.
So you use a function.
So yeah, essentially. And then we've also, since the AD converter doesn't have a microphone preamp built in like the PMOD mic did, we're just using a computer as a microphone preamp, and then we send
Okay, so it's kind of offline.
yeah.
Yeah.
Okay. So that's how you do it.
Yeah.
Pretty much trying to get rid of the most amount of noise we possibly could. Because the PMOD mic captured way too much noise on the outside and we weren't getting consistent data at all.
Other questions?
And then if you guys want to come to bench one.
First off, you can see on the display it'll show you the frequency of the signal that's currently being received, and then it'll show you what note that signal is closest to, and then how far off from the note you are. So now we're sending a tone from the iPhone over this cable into the AD converter, and we're sending it at 440 hertz, which is an A, and it's telling us we're not off at all. So if we start skewing that a bit,
A sharp or something.
so now we're at B flat, which is A sharp.
Mm-hmm.
So you can keep dialing up. I think the RFFT algorithm tops out right around 3200 hertz and bottoms out at about 200, which is plenty for tuning up a guitar. So you can keep dialing that all day and it'll keep giving you accurate frequency results. So right now the phone's reading about 2093 and this is reading about 2089, 2090 now. So that's what we did to test it, to make sure that we could get accurate results.
Did you know
And
about
if you
that
don't have the-
before you get started?
Yeah, yeah.
And if you don't have the cable plugged into the phone, you can actually hear the noise coming out. So originally we were trying to test the noise coming out of the phone into the PMOD mic, and it just wasn't consistent enough data for us. So when we connected it right with the wire, it was pretty much dead on.
And then,
Yeah, that PMOD mic is really crummy.
yeah.
Yeah.
Okay, get some good results here. Okay, there we go. You can see when we've got an actual outside signal, it's not quite as dead on as it is when we feed in a signal from a tone generator. Okay, that's pretty problem is since our there you go, there's the D. Since the FFT takes so long, the key is catching it when it's pulling for input and not when it's doing calculations. So it's it's a little iffy, but you can get good data out of it if you're persistent.
You found that it gets close, but you might have to play the note for a couple 5 to 10 seconds before it actually registers and picks up to the actual frequency on the tuner. It doesn't pick it up right away because it has to go through the calculation a couple times to get it to work out. But like you said, if you're persistent and you sit there long enough, it comes with a note pretty close to it.
So if you batch it up, basically is what you're doing.
Yeah.
Taking the data in, then you put it out.
Yeah.
To the FFT and all that.
Yeah.
So it seems to be quite quick.
Oh,
Second.
yeah, it's
pretty
roughly
fast.
a second and a half. Yeah.
So you think the issue is where they capture the data for the FFT?
Right.
So you need some sort of threshold
Yeah.
that would then start the window of the actual signal that you want to use. That would be very helpful.
Yeah, that would have been a better way to do it.
Because another problem is the amount of data that you capture. If you capture for a longer amount of time, you get a lot more data, but then it takes a lot longer to run it through the FFT algorithm.
Yes.
So you have to wait a lot longer before you can capture again, but you capture for a longer amount of time, so it's easier to get a note. So we try to come up with a happy medium, and it's actually a fairly short capture time, but because it goes through the algorithm faster, it refreshes quicker.
What is your
So-
window that you're using? Relate to time.
We're taking 512 samples, and I think that takes roughly 22 microseconds or something ridiculously quick like that.
Okay, so that's
Yeah.
probably why.
Yeah.
Yeah.
It's sporadic then.
Yeah,
You're probably taking silence.
Right.
because it's really fast capture period. But if you make it too much longer, then your FFT algorithm takes
Right.
absurdly long.
But you
So-
know, some of those things have thresholds that won't record until you're above a certain amplitude.
Right.
Yeah,
For a period of time, and then it records.
yeah.
So that would solve that.
That would solve that a lot,
Yeah,
actually.
but all it takes is time, right?
Yeah. Time and persistence.
Yeah. We didn't have a lot of. Oh, good.